Okay, let us continue. Okay, so let us continue with the factorial designs. Okay, so in the factorial designs, we have a go through the special case under the factorial design is a 2 power of k factorial design. So means that you consist of the k factors. Each factor contain 2 levels. So this one is called the 2 power of k factorial designs. So I have gone through with you the a few examples. Okay, so make sure that you know what is meaning by the contrast. Okay, I have mentioned to you that in the 2 power of k factorial design, so we can write in the sign of the plus minus sign because it consists of 2 levels, either it's low level or high levels. So therefore, we use a minus and plus sign to represent the lower level and higher level. And then I also mentioned to you that what is the notation for the 1, A, B, C, and so on. Okay, 1 is stand for all the factor levels at the low levels. So we use the notation 1. The A is means that only A at the high levels. The rest of the factors at the low level. So we use the small letter to represent it. Okay. So from here, we can calculate out the sum of square in the 2 power of k factorial design. We can use the sum of square to calculate the using the following formula here to calculate the sum of square. So the sum of square will be given by the contrast square divided by n times the plus minus sign here. Okay, for the contrast of the factor A will be the minus 1 plus the A minus the B and so on. So this one is a contrast. You can refer back what you have go through before. I also show you that this is a special formula for the case of the 2 power of k. I have shown you the proving. And then also we will know that is it this one is the effect is a positive effect or the negative effect. Okay, so they also can be obtained from the contrast is divided by n times 2 power of k. So this one is a very true review all. Then after that, I also have show you about this example. The 3 factors with each factor is a 2 levels. So therefore, you have a negative sign and a plus sign. Okay, and then for the each treatment combination, they repeat for 2 times. Okay, the number of replicate is twice. So the 1 here is represent the total for the first the total for the 2 replicates under the treatment, the first treatment combination. For the second one, A is stand for the total of the second treatment combination of the total of these 2 values. Okay, and so on. These are the values we have. Okay, so to calculate the effects, as I mentioned to you, these are the contrasts. Okay, the contrast will be given by here. This is a contrast under the factor A. So you also can be list down the contrast for the factor B, factor C, and so on, so that you can calculate the effect. So for this case, the effect is a negative. Okay. So in general, the effect will calculate as a contrast divided by n times 2 power k minus 1. Okay, so we can calculate all the effect out. Okay, so after that, we can be calculate out the effect is given by here. The rest of the effect will given by here. Then as you observe that the factor A with the negative 101, the effect is quite negative. Whereas the factor B, the effect is quite small. It's nearly the value 0. So this one, the factor C also have a positive effect. Okay, so for the large value of the effect, we will expect that they contribute, they have a highly significant. Okay, but anyway, we still need to test the hypothesis to confirm it. Okay, so from this diagram, from the effect itself, you can calculate the sum of square. So the sum of square for the factor A, factor C, and the factor AC is considered as the large. Okay, for the factor A, factor C, and the factor AC is considered as very huge. Okay, the values. So the percentage of the contribution to the overall sum of square will be given by here. As you can see, the factor C will be the 70%. Whereas the second one is the AC is a 17%. The factor A will be 7%. So these three components will contribute to the majority of the factor effects here. Okay. So this one from this diagram will show you that we roughly will know that factor A, factor C, and the factor AC tends to significant. Okay. So it means that they are the important factors. So from the analysis here, we will carry out the ANOVA tables. Okay, the analysis of variance tables for all the factors here. Then it's as we expected, we can see that the factor A, the p-value is 0.0027, factor C, and the factor AC. These three factors is a significant factor. Okay, so we know that the factor A, C, and the AC are important. Okay, in the analysis. Okay, so furthermore, we can use the factor A, C, and the AC to form the linear regression model. So that one I will go through with you in the next chapter. Sorry, not the next chapter, the following in the following chapter, not the next chapter. Okay. So this one is here. Okay. This one is if you are using the ANOVA, you also will get the similar results. Okay. It will show you that it's significant or not significant. Okay. And then this one is the output from the Minitab. So the Minitab result here is a effects, and then go through later. Okay, not today, but it's under the regression model. We will go through it later. And then this one is the analysis of variance table. Okay. So about the box and whisker plot, about the normal probability plot here, I will discuss after I go through a few slides here. Okay, so this one is the goodness of fit for the residuals. Okay, so just now we have gone through a few of the parts where we have 2 power of k factorial designs. Then we calculate sum of square. We calculate the effects. Okay, so in this slide, we would mention to you that if you want to judge that whether this factor is a significant, instead of the carry out the ANOVA table, instead of carrying out the ANOVA table similar to here, okay, we also can have another alternative where we use a confidence interval for the effects. Because before that you have calculated the confidence the effects, but from the effect itself, we know that the value is large. But whether it's a significant or not the significant, then we need to carry out the hypothesis test. So confidence intervals will help us to test it also whether this effect is a significant or not significant. Another alternative will be the normal probability plot. Okay, you are plotting the normal probability plot. The normal probability plot will given as this thing is a normal probability plot. Okay, so from the normal probability plot, we also can be identified that whether the factor is important or not the important. Okay, so these two is 2 parts is where we can consider. Okay. So the first one, if you confidence interval for the effects, we need to know the effect itself, and then we also need to know the standard error of the effects. Okay, so how to get the standard error of effects? We let the SI be the variance within the one of the for the here is a sum out from the 1 until the n. Okay, for the Yij minus the mean for the first the treatment combination I here, where you have a first factor level, the second factor level, and so on. Okay, so where the I will be equal to 1, 2, 3 until the 2 power here. Okay, so the I here, where you have all the observation here, is the estimate of the variance for the I run. Okay, so we call it SI. So the two power of k variance estimate can be combined to give the overall variance estimate. Okay, so if we combine all together, because for the I is equal to 1 until the 2 power of k, okay, so we can be combine all the variance together. So we just have a sum of the summation of the I is from here I from 1 until the 2k, then divided by 2k. So this one is an overall S square. So this one also is your MSE, okay, your mean square error. Okay. So from the mean square error here, the MSE, okay, so we know that the variance for the effects, the effect is given by contrast divided by n times 2 power k minus 1. So therefore, we can take out the constant, then it square out the variance for the contrast. So the variance for the contrast is actually is equal to the sigma square here. Okay, the variance for the contrast here will be equal to the sigma square here. Therefore, the variance for the effect will be given as a, okay, the variance for the effect here will be calculated as a equal to the n times the 2 power of k sigma square. So maybe here I think I have made some mistake here. Okay, yeah, the variance for contrast is not the sigma square alone. Actually, the variance for the contrast, the variance, because you see the here is a different. So maybe I will write in this one first. Okay. So the variance for here will be equal to the 1 over n times 2k minus 1 square. So the variance for contrast will be equal to n times the 2k sigma square. Okay, the variance for contrast of there is equal to n times 2k sigma square. So if you simplify out, you will get the following form. Okay, n times 2 power k minus 2 and then multiply by sigma square. Okay, so the variance for contrast will be given by this form. And then from here, once we get the variance of the effects, we take the square root, then we get the standard error of the effects. We're given by the 2s. The s is to estimate the sigma square. Sigma square is unknown, so you use a sample standard deviation to estimate it for the sigma. Therefore, you have a 2s divided by square root of the 2k. Okay, so of course the 2 power of k minus 2 will move it here. Okay. So finally, you can be construct the confidence interval for the effects. So the effects plus minus the p multiplied by standard error of here, the standard error of the effects. Okay. So from the standard error of effects here, we will have a is equal to the effects plus minus the standard error itself. So all the standard errors will be the they standard error multiplied by t, they will get the consistent the same. Okay, so what we need to observe is those of them is from here. If you observe this thing, this one is a negative value. Okay. You will get your negative value. So this one is a negative 101.625. Okay. So this one is the first one, the confidence interval. You will get the both of them negative. This one is you get the one of them is a minus, another one is a plus. You get the one negative, one is a positive. You get is this one 62.195. Okay, so this one is the second one, and so on. You can be calculated out. So what this result will tell you whether the effect is whether this factor is significant or not significant. In fact, the hypothesis testing will testing that whether the effect will be equal to 0 versus the H1, the effect not equal to 0. Okay, so if the effect is equal to 0, their effect is not significant. So when we get the confidence interval, we will check it out. Is it the 0 is covered in the interval? So both of them negative. The 0 is somewhere around here. The value 0 here. Both of them negative. Therefore, the first factor here, we reject the null hypothesis. So we know that the effect is not equal to 0. Means that this effect is significant. Okay, this factor is significant. For the factor B, one negative, one positive. So the 0 will cover inside the interval. The 0 will inside the interval. Okay, so means that we do not reject the null hypothesis. Therefore, the factor B is not significant. So it's not significant here. So you also can be check this one. 306 minus a 54, you get the positive value. 306 plus the 54, you also get the positive value. So both of them positive, where the 0 is not in the interval. So therefore, this one is a significant. Oh, so it is related to the hypothesis testing. The confidence interval will be related to the what is your hypothesis, null hypothesis and alternative hypothesis. So you just calculate out the values. You can check whether the 0 is inside the interval or outside the interval. So if they're outside the interval does not cover 0, means that they are reject the null hypothesis. So you will go for the effect is not equal to 0. Okay, so effect is not equal to 0 means that this is an important factor. Okay, so the same result, the similar result you will have from here. Okay, the similar result you get from this here, you will identify that the factor A, the factor C, and the factor AC. So if we recall back here, after we construct confidence, we can check it out. This one negative 154, negative 54 is negative. 3 plus 54 also negative. Therefore, this one is significant. So if you check it out all of this one, only these 3 will be consistent with the ANOVA table you have. So we can be using the factor effect here to test the hypothesis. So this using the effect to make the decision whether this is an important factor or no. Okay, so this one is one way you can do that. Okay. The second way, okay, before I go, the second way, what you can do is about plotting the normal probability plot. Okay, so the normal probability plot is very useful when you want to judge that whether this factor is important or not important. Okay, so the normal probability plot, you plot all the effects inside. Okay, you plot all the effects inside the normal probability plot, and then you can be check it out whether this factor is important or no. So you can see from this one. This one is why we're plotting the normal probability plot. So of course I do not ask you to do the plotting of the normal probability plot using manually, because you need to have the graph paper for the normal probability plot. So therefore, if you want to plot the normal probability plot, we can use the software to plot the normal probability plot. So over here, under the normal probability plot here, if you use a Minitab, they plotting the normal probability plot, then they can identify for you. Those of the factor is far away from the line here is considered as a significant factor. So in the Minitab itself, they can identify A, AC, and the C considered as a significant factor. Okay, so this plot will be very useful when you deal with the n is equal to 1. Okay, so that one I will go through it later. Okay, through in detail about the normal probability plot later after you go through here. So over here, deal with the calculation one is only the confidence interval, where you construct the confidence interval for the effects. Okay, then you can identify the important factors. So about the normal probability plot, to you is just one of the example. Okay. Later on, I have some more the normal probability plot where you can see that when you have n equal to 1, the normal probability plot will be very important tools to identify the important factors.
Sorry, doctor.
So in yeah.
For the confidence interval just now, right?
Hmm.
The BC and the ABC, if from the calculation itself, it would include 0 as well. So does that mean that from this result, it is
BC.
yeah, BC and ABC.
Wait, negative. Let me see whether I copy the wrong one. Negative.
Because one is negative 56 point something, the other one is 52 point something.
Yeah, one is a negative, one is a okay, one is negative, one is positive.
Yeah, so it includes 0 as well. So does that mean that it is insignificant? For
okay, they should be let me check. If they include the 0, then they should be not the if they include the 0, they should be not significant one.
Not significant. Or not doesn't mean okay. I think
so you have a negative, you have both of them negative, correct?
Okay.
So because the 0 is the input here. So same like here, this one is important, this one the 0 is here. So therefore the A is important.
Okay.
This one is one negative, one positive. So the 0 is inside. So if the 0 is inside, the effect is 0. Means that the effect is not important.
Okay. Okay. I think I
okay.
Yeah. Okay. Thank you.
Okay. Yeah. Sure. Okay. So let me continue. So in general, the 2 power k factorial design, we also can be performed similar to the factorial design. Okay, where you have many factors. Okay, but the important thing is when you have many factors, where you have k factors here, then you will involve many of the iteration, the 3-factor iteration, 4-factor iteration, and so on. You have many of the factor iteration. So this one will be make your whole thing will be very complicated. Okay. So basically, in the analysis of procedure of the 2 power k, this one is just a guideline of the 2 power k factorial, factorial design. So the first one is we estimate the factor effects. Okay. So from the factor effects, we know that this factor is a positive or the negative. Okay. That from the factor itself, we will roughly know that which one are the important factors. Okay. After that, you can be formed the initial model. Okay, in the modeling, your model will keep changing. So therefore, you will try to get the starting model first. So the starting model maybe will fit the full model. Full model means that all the factor will put in the model. Okay, so if you have a replicates, then you fit to the full models. Okay, if you have a replicates, you put the full model is no problem because you can estimate all the factors levels for the main effects, the iteration, 2-factor iteration, 3-factor, and so on. All you can do that. But if your replication is no replication, then of course it's not the full model anymore. So this one you will assume, if you still remember, you can be do is one way is you assume the high order iteration is not significant. Okay. You do the assumption of the some high order iteration is not important, then you can be use that high order iteration as your error. That one is one possibility. Another thing is if you have n is equal to 1, if your n is equal to 1 without replication, then you can be use a normal probability plot of the effect. So this one is just now I mentioned to you. Later on, I will show you to you about using the normal probability plot to identify the important factor through their effects. Okay, so you plotting the normal probability plot of their effects, then you can identify those of the effects far away from the line will be considered as important factors. Okay, so like just now I show you the example, the mini tab can be well. Okay, so from here, once those of them are not the significant factors, then you can use them as your error, because your n is the no replication means that your n is equal to 1. So therefore, you need to have the SSE from other sources, from those of the not important factors, or those of the not significant factors. Okay. After that, once you have identified it, you perform the statistical testing. Okay. So if you test it out, if the fact is still not significant or significant, then you can remove those of the not important. You refine your model again. Okay, so you cannot say the first final models. Even though you do for the any type of modeling, the modeling you always will try and error until you satisfied with your final models. Okay, so even though you have a final models, the model may not be used forever. Sometimes if they have certain cases will happen, so they need to refine the model. So the model will always refine, and of course you are checking your residue and then interpret your results. Okay, so actually this process is not only applied here for any of the statistical models, you also need to define the model. Okay, so this one is I just show you the diagram of the sum of square. All the sum of square what you have. If you have so many factors, then all you have these are the sum of square you have. Then clearly all the degree freedom of the sum of square because of the two factor levels. Therefore all of the degree of freedom is 1. The total degree of freedom will be equal to n times 2 power k minus by 1. So the remaining one will belong to the error. So now we go to the special case where we will try to get the normal probability plot. Okay. So in the single replicate of 2 power k factorial design, there are 2 power of k factorial design with one observation at each corner of the cube. Okay. So the cube here, I use a graph to represent. The cube here is referred to the let me check. Okay, the cube here, I show you the cube here. The cube here is referred to this thing. It's referred to where you have a factor levels here. Okay, you have you can represent in the cube form. So the unreplicate 2 power of 2 power k factorial design is also sometimes called the single replicate of the 2 power k design. So they are very useful. Of course, if you have a n is equal to 1, you need to take the risk. Because you have the accuracy of your data, the first thing. Because you only measure one observation, then you make sure that your observation must be when you do the measurement, you must carefully measure. Okay. And then if you have only one observation, you need to give out certain information so that you can perform the analysis. So in the single replicate of 2 power k factorial design, you are lack of the replication. This one will cost you for the internal estimate of the error. Okay, so with no replication, fitting the full model will result in the 0 degree of freedom for the error. Okay, so therefore you have a few ways to do it. One way is I have mentioned to you, I repeat again, is a pooling high order iteration to estimate the error. For example, you study is 3 factors. You have A, B, C, you have AB, you have AC, you have BC, then you have ABC. Okay, so if you only run for the single replicate, so therefore you can consider this one as a not important factor. Then you can remove it, pull it to the error. So you can treat this one, the sum of square for the ABC is as the error. Okay, so this one is the information you will lost because first thing you do not know ABC is considered significant or not significant. You do not know. Okay, so one possibility is we try to pull out all the higher order iteration, because if you have a higher order iteration also, sometimes very hard for you to interpret the model. So one possibility is we pull it to the error so that we can test test for other factors. The first thing. The second thing is the ABC also is a high order iteration. Then they will make your model complicated. Okay. So if you do not suggest for the first one, then you can use the second one. Okay. To consider which of the effects are significant. So by using the normal probability plotting. So this technique is suggested by the Daniel in the year 1959. Okay. So how to do the normal probability plot? I believe that this thing is just I put it here is just a manual do it, but I do not think that you need to do it manually. Okay, if we do not have any prior knowledge about the high order iteration, okay, if you do not have any knowledge about high order iteration, which one is significant or no, then you can consider use plotting the normal probability plot of the effects. Then you check it out whether they are considered as significant or not significant. Okay, so how to perform the normal probability plot? Of course, you need to calculate the PJ. You need to order your effects from the smallest to the largest, and then you calculate the corresponding PJ here. So you just calculate this quantity, and then you need to plot in the normal probability plot paper. Okay, if you do it manually, but I do not think that you no need to do this thing. Okay, as long as you have an effect, you can be plot using the others R software, any software to plot in the normal probability plot. So therefore, you no need to have a normal probability papers. Okay, this one is one way. Another way is they can be considered the absolute value of the effect, because your effect can be positive, can be negative. So they use a half normal probability plot papers, okay, to plot it out for the what is the total effect you have. But this one is take the absolute value of the effect. So the Daniel part will mention that the effects that are negligible are normally distributed with the zero mean and the variance sigma square, and will tend to fall along the straight line on the normal probability plot. Whereas the significant effect will have non-zero means and will not lie along the straight line. So those points where they far away from the straight line is considered as a significant effect. Not necessarily they must be fall exactly on the line, because all the data you have is the empirical data. Okay, so therefore, as you can see from this example here, even though this point is not on the line, but those of them is considered as they are quite close to the line as compared to these 3 points. Okay, so they have a calculation of the using the software they have calculate for you. Then these 3 are the factor is important. Okay. Okay. So let us go through the following example. Is this one is for the single replicate of the 2 power of 4 factorial design. So where they have 4 factors consists of the A here, temperature, B and C, and the D here. Okay, they have a pressure, the concentration. Okay, so for the study of the 4 factors, okay, so here are the 4 factors you have. So these are the results you have run it. Okay, so if you observe the table here, you have a standard order form where you have a minus, plus, minus, plus, and then after that you have a 2 negative, 2 plus. Then after that you have a 4 negative, 4 plus. After that you have a 8 negative. Okay, 8 negative, 8 plus. So you can see the pattern is there. Okay, so this one are the 2 power of 4. So it's a 16. You have a 16 triple combination. So the first one is all at the low level. We give the notation as a 1. So when they run the experiment, they measure the values. the value is 45. The filtration rate is 45. They measure under the second treatment combination, they will get the 71 and so on. So here are the results they obtained through the experiment. Okay, they run all the treatment combination. So it's a diagram to show you that in the cube form, they will represent in the factor A, factor B, and so on. Okay. So from here, as similar to just now, we calculate all the factors effects at the same time. We can calculate the sum of square, but we are unable to test the hypothesis because your sum of square for the error will be equal to 0. Okay, because you are unable to do that, you only can get the sum of square from the A until the ABCD, all the sum of square, and then you check percent of the contribution. We can check it out. This one will contribute for the 32%. This one will be 14%. This one is a 6% here. This one AC will 22%. The rest of them is quite small. AD also is 19%. These are a few things is a quite high percentage. So we will expect that the A, the C, D, and then the AC and AD are quite important factors here. Okay, but anyway, we still need to proceed with the checking. Okay. So this is a Minitab result, the R results only. I just want to make sure that my data is keyed correctly. Okay, so this one is a sum of square. Just now I have it. If I run the ANOVA table, I only can have a sum of square, mean square, all divided. I unable to process with the ANOVA because the n is equal to 1. They don't sum of square for error. Okay. So one way is can be, if we cannot assume all the high order iteration is not significant, we have two options. If we can assume the high order is an iteration, then we can be use that one as a sum of square for the error. Okay. But if we do not have any information, then we are plotting the normal probability plot. So through the normal probability plot here, we can identify AC, ACD, and the AD are important factors. Okay. So from here, we know that these are the factors. Then we can proceed with the analysis of the weight. Okay. So therefore, we can be calculate. This one is to calculate the effects here. I calculate the effects here. Okay. Of course, the coefficient we will leave it for the future. We will discuss later. Okay. Then this one is if you want to know how I calculate the normal probability plot, I will show it to you. Okay. We order the effects from the smallest to the largest first, and then we calculate the PJ for each one. Then after that, we plot it in the normal probability plot papers. Okay, not the ordinary graph paper. It's the normal probability plot papers. Then you will know whether which one will fall on the line. Okay, but now with the statistical software, you can do the plotting. So if we do using the Minitab, they will show us here the AC, C, D, AD, and the A. This is a consistent result with the just now one. They say that these are the important factors we consider here. Okay. Then of course, this is a diagram. If some of you may want to plot for the half plot, they will also give you the similar results. Okay. So since these are the important factors here, okay, since these are the important factors, then we can be form the ANOVA table by only considering all these all these factors here. The rest of what is the rest of the factors, the 2 iteration, 3 iteration, 4 iterations, all of them, they will assign it to the error. Okay, so therefore you square now, you can have an error to be had. Okay, you have a residual error right now. Okay. So those of the not the important one, they will put it as an error. So therefore, you can be test the hypothesis of the main effects. They are significant different. Of course, in the Minitab, they do not present for you one by one. Okay, they do not present the result one by one. Okay, they only present the result in the whole in the whole graph of here is the main effects, the two-way iteration. Okay. So if we present in the ANOVA table, this is an ANOVA table we have. The factors here we considering is should be just now the A, C, and then D. We only consider is a AD and the AC here. Okay, why these two is purposely they put it here? Okay, because as I just now mentioned to you that if we're using the normal, we will identify is only these are the 5. Okay, we can be stick to these 5 of them, and then the rest of them we can be throw it to the error. But in this example here, some researchers will think that the CD and the ACD will be important. Therefore, they leave it in the model. Okay, but if you want to base on the just now the normal probability plot, then these are the factor will remain in the ANOVA. The rest of them, the rest of the factor will throw it to the error. They will form your error. Okay, but there is a reason why they put it here one. Okay, because they put it here because they think that the A and the C are important. So A, C, D is important. So they also treat the CD also is an important factor. Okay, so this one I will tell you in the response surface methodology when we form the equation. So for the time being, we only concentrate on the here. If you identify those of the important factor, you just put all these things in one table. The rest of them, you just throw it to the error. Okay, inclusive here, you group. Okay, so you can form your ANOVA table to check whether it's really significant or not significant. Okay, but as I mentioned, in this example, they will put it separately because they want to include this one as the main factor, as the important factor in their model. Okay. So because your the iteration factor will be important. Okay, because just now from here, the AC and AD will be important. So these two will affect your result of the A, C, and the D. So iteration will be important. Then you cannot interpret the A, C, and D separately. So in this diagram, we are doing the plotting of the main effect as an iteration effects. So if you observe here, if we want to get the maximum value or the largest value, then we consider the positive here, the positive here, the positive here. If we want to have a large value of here, if we want to have a low value, then we should choose the negative level, and negative level. Here, if we choose the maximum, if we want to get the maximum value, the large value, we will choose 1, 2, 3 here, or the large value here. So, but because of the iteration is significant, then as you can observe here, when the A at the positive, to get the high level of the large value, choose the C is in the negative. You cannot choose the C is a positive. So if you only interpret for this graph for the main effect, then you will lead you to the wrong conclusion. Okay. Similarly, over here, level and the high level of the A. If you choose the A at the high level, of course D also you should be choose the high level. If you wish to have a A at the low level, then you should be choose the negative. The D is a the D is a positive, but these two is not different very much compared to here. So this diagram, this 4 diagram will tell you that how important is your 2 iteration, 3 iteration. But if you have a 3 factor iteration, you want to draw the graph, I think it's very hard for you to illustrate using the graph. So means that if your model consists of the many iteration, the 2 factor iteration, 3 factor iteration, and so on, then you will make your interpretation will be very difficult. So therefore, you will consider this one. They will to pulling the high order iteration to estimate the error instead of leave it in the model. Okay, because when you have a many of iteration, you want to interpret one by one, it's very hard. Especially your target is want to know about these other factor, which factor are important. Okay, and then at the factor A, which level you should be considered. So this one is about the plot here to interpret for the important thing of the iteration. And then this one is should be the examples under this case. Okay, this one is show you that if you do the transformation of the data set, if they do not fulfill the condition, then you do the transformation, or without, if you leave it for the no transformation, you can see that you will lead you to the different conclusion. Okay, so this is an example for the first one. Also is a 4 factors where they get it from the paper in the year 1976. So they consist of the 4 factors. You can refer to the textbook. You can read the detail of the story. Okay. So this one is an illustration of the data set. The data set here. Okay. So this plot will show you that if you are using the plotting of here, the first one is show you the plot of here. Okay, the normal probability plot here will show you that which are the important factors here. So from this plot here, we can see that the B, C, D, and the BC and BD are important factors if using the normal probability plot. However, if you checking their assumption of them, okay, you checking the residue of them, they were far away from the here. So here is a, you have here, you have a far away here. So this one is a normal, the normal probability plot. It seems that they are, may not be the normal. Okay, then some more over here, the residue versus the predicted value. Here, the variance is a look like it's not constant because our model is assume that it's constant variant. Okay, so therefore, if they have this type of the shape here, then the assumption, of course, the data is do not fulfill the assumption. So what we need to do is we do choose the suitable transformation. I cannot tell you what is a suitable transformation. So you need to do the transform of the data. How do you choose the transform of data? Sometimes you may choose the x squared. Then you need to try for the log x. You take the exponential. You need to choose and you need to try a few times. Then you only can check whether the assumption fulfilled or not. Because you cannot just try one time, then you expect your answer, you get it. Okay. So the transform, the final conclusion. So it, because of course this one, the result from the example, then of course they will choose the transformation of the long y. Okay. Okay. They transform the data to the long. They found that. Okay. After they transform to the data, you can see that before I go through the slide here, the normal probability plot, you can check it out, the normal probability of the residue. So now I refer to residue. The normal probability of residue is quite reasonable. Okay, where they fall on the line as compared to this now, they have a different shape. Okay, then at the same time, the residue versus the predicted, the variant is not same like just now. The variant will be quite consistent. This quite consistent of the shape here. Okay, so after you, this is a result you can reconsider. But if you observe it based on the transform, you only can identify these are the 3 important factors. Whereas if we, without checking the assumption, we just directly go to plot, we can see that these are the model we consider. We also consider BD and the BC are the important factor, but this one may not be the correct answer because your model does not fulfill, I mean, you set the model there, they do not fulfill the assumptions of the model here. Okay, so therefore, this assumption is not fulfilled, they will give you to the wrong conclusion. Then after that, you do the transformation of the data, you can get it out. The result is only these 3 factors. So those are the iterations significant. So since the only main factor are important, so when you would want to interpret your result, it's much more easier. Okay, so this is an example. Then I think the author writing the books also, they can find the very good example. Because in reality, sometimes you need to transform. May not be the first attempt you will get your graph will, or the residue will fulfill all the assumptions. So if they do not fulfill, you still need to try for the second attempts, the third attempts, and so on. Okay, until you think that is satisfied. Because sometimes you also try many attempts, they still cannot get the very satisfied results. Then you choose the best one. Okay. This one is show you that the why the data, if they do not fulfill the assumption, then the residue will be the violation. Then they will lead you to the wrong conclusion or different conclusion. I cannot say it's wrong conclusion because you can have different models. Okay. So finally, this one is the analysis you have. Okay. So these three factors are show that is significant. Okay. After you log transformation. Okay. So this one is should be the last slide of the 2 power of k factorial design. So under the 2 power of k factorial design, you need to know how to how to calculate the sum of square, how to calculate the effects, and then what are the techniques you can do for the testing of the hypothesis, whether that factor is important or not important. You can use the normal probability plot. Just now I have shown it to you, or you can consider using the confidence effects, or you can consider assume certain high order iteration is not significant. But how do you assume? That one is quite subjective. Okay, most of the time we will consider 3 factor onward. We do not consider in the model. As you can see, if you have a 3 factor iteration, 4 factor iteration, they will make your interpretation very difficult. Okay, so you can try for the different attempts. Okay, you can try for the different techniques, and then you gather all the information. Then you only make your final decision of your model. So your model may not be based on one output, then you make the decision. Okay, so therefore, when we deal with the modeling, they have many many different. We look at the different from the different aspect. Not only looking at the one aspect, then you finally decide this is the best model. Okay. So after this one is to be end of the chapter number 6. It's a 2 power of k factorial design. Okay. So I have uploaded this is a chapter number 7 also. We will also concentrate on the 2-level factorial design as well. Okay. So this one is the following chapters we are considering here. Okay. This one is called the blocking and confounding system for the 2-level factorial design. Okay, so we still concentrate on the two power k case. Under the 2 power k case. And then if you still remember, I have mentioned to you what is the blocking. Okay, the blocking, I have mentioned to you the principle of the blocking. And then from the idea of the blocking, we will go for the confounding system. Okay, we will go for the confounding system. Then you can see what is meaning by the confounding system. Okay. So the first one will be the introduction of the blocking principle. If factors where they will affect your results, then you call it as you using the blocking techniques to remove it out, or you try to extract out the Nelson factors here. Okay, so by using the blocking principle. So this one I have introduced for you before that. Okay. So I show you the first example is for the blocking first. Then after that, we will go to the confounding system here. So under the blocking and the confounding here, under the blocking here, I show you the first example. For example here, okay, you want to run your experiment. 2 power of 2 factor is a 2 power of 2 power of 2 2 power of 2 factorial design. Okay, for the 2 power of 2 factorial design, where you consist of the 4 treatment combination, you have a 1 A, B, and AB here. So because you have a 3 batches of raw material, where all these 3 batches of raw material, they have a different effect. So therefore, the 3 batches of raw material become the block 1, block 2, and the block 3 here. Okay, so this concept will be similar to what you have learned before in the chapter number 5. Factorial analysis is no different. The block is the same concept. Okay, just your data now you consist of the block here, where they are under the Nelson factors here. Okay. So if you have a blocking here, of course your model will be in the following one. If you have a blocking here, your model Yij, okay, will be equal to the, this one is not only the single replicate, it's here is only the 4 experiment here with the single batch of the here. Okay, so this one is I consider it as a just the Yijk here. Okay, so where you have a mu plus a tau I plus the beta j. Okay, plus the third one will be the block. So the block I will use the gamma k plus the epsilon ijk. Okay, so this one is the block. Okay, the blocking is here, where you consist of the block number 1, block number 2, and the block number 3 here. Okay. So in this example also, we have all together is a 12. We have here is a, you have a 12 is a 3, 3, 3. Is because you have 3 factors here. I mean the third one is considered as a Nelson factors. So you have I is for the first factor, the factor A. We use the notation at A for heat. This one is for factor B, and then this one is for the blocking here. Okay, and then the epsilon ij, k will be your error here. But how many replicate in this example? How many replicate there? For each one, the 28, how many of them? So if we list it, if we have the data here, okay, we have a data here is a, okay, you have a 3 replicate here, okay, you have a 3 replicate of here, okay, 3 replicate means that the total here is get from the 3 replicate. Therefore, when I want to write the model, I should have another subscript here. So this one is the L here. So the I here is for the factor A, where the I here is consists of the 1 and the 2. The J here also you have a 1 and the 2 only. The K here, the block, you consist of the 3 blocks. Therefore, you have a 3 levels here. So the I here is equal to 1 and the 2. The J, 1 and the 2. The K, you have a 1, 2, 3 because you have a 3 level of them. The L here is number of replicate is 1, 2, 3. Okay, you have a 3 replicate here as a question mentioned to you. They run for the 3 replicates. Okay. Because from the data, hello.
Sorry.
Yeah.
What about the interaction terms?
The interaction term, yes, you need to include the interaction term. This one is I just write down for you. Yeah, you need to have a it. Okay, I will write it down. Okay. Yeah, thank you. So you see, you have a main effector, you have a the factor A and the factor B, and then this one is a Nelson factors here. Okay, when we consider the model of the factorial design, the Nelson factor do not interact with the all these things. So therefore, as just now your friend mentioned, is you have a iteration term here, ij, and then plus the last one will be the epsilon ijkl. Yeah. Or the iteration term will be here is the AB. Yeah. So the Nelson factor, we do not iterate with the main factor itself. Okay. Okay. So you have a I, J, K, and the L here. So this one is a complete model for this case. Okay, so over here, because you have a vector AB, and the block, therefore calculate a sum of square. We should have a sum of square for A, sum of square for B, sum of square for AB, and then sum of square for block. The remaining one will be the sum of square for the error. Okay, so from here, if you want to calculate the sum of square for the block, it's just as usual formula where you have a bi square, the b square, the total of the block square divided by 2k. Okay, then minus by the grand total square divided by n. Okay, so you can observe it here. This one you get it from the average of the four values here. Therefore, you have a 4 here. Okay, so in the analysis of variance table here, where you have here is the blocks here, where you have a degree of freedom should be the b minus 1. So you have a 2 factor A, factor B, factor AB, all the degree of freedom it should be 1. Total degree of freedom is 12 minus by 1 is the 12 minus 1 you get the 11. Therefore you will know your error degree of freedom will be equal to 6. Okay. So from here, you can be analyze your factor A, factor B, and the factor AB. So you can observe it that this one will be the significant, this one will be significant, this one is not the significant because 0.6, 0.2 here. Okay. So therefore, we can do the analysis of the A and the B. We can check further which one is the important factors. Then you can because it's only 2 levels. Therefore, you can be checked. The result is significant. Then if you have only 2 levels, for example, the factor A is a negative and the positive. Okay, so if you get this one, if you want to get the height value, then of course you choose this one because only 2 levels. You no need to perform the LSD, the Fisher-Tukey test, all these things no need. Okay, because only 2 levels. You from the graph you already know which one is here. From here, they tell you there is a significant difference. So therefore, you from these two, you choose the one if the height value or the load level, whether you want to get the maximum or the minimum problem. Okay. So this one is similar to the previously what you have studied before. The only thing is under this section, I repeat it again the blocking. Okay, for the case of the 2 power of k factorial design. Okay, the idea will be the similar thing. Okay, now if let's say you have a block here. Okay, for the every block you run the 1 A, B, and AB. All the treatment combination you run all. For the block 2 also run all. The block 3 also you run all. Okay, if you have enough material to run, then of course you can run all. Okay, but if let's say you do not have the enough material to run, okay, so this one is we will consider running smaller or the part of them. So this one is called the confounding concept will come in. Okay, so what is meaning by the confounding in the 2 power of k factorial design? So in the many problem, it is impossible to perform a complete replicate of the factorial design in one block. So in one block, you have a 4 treatment combination to run all. You can't. You only can run part of them. So therefore, the confounding system is a design technique for arranging a complete factorial design in the block, where the block size is smaller than the number of treatment combination in the in one replicate. Okay, so means that your block the block size will be smaller than the number of the treatment combination, or we can be say in this way, we construct and analyze of the 2 power of k factorial design in the 2p complete blocks, incomplete blocks, where your p must be less than the k. Okay, consequently, the design, this design can be run in the 2 blocks, 4 blocks, 8 blocks, and so on. So there is a limitation. You cannot simply you want to run the 3 blocks. Also, it cannot. they must be have some limitation. If you do not want to run the whole experiment all together, okay, I mean the completely same like this table, you don't want to run combination, then you run less. Okay, so if you have a 4 treatment combination, you want to run less, then of course you can run it less. Okay, so this one is here. If let's say, for example, we have a 2 power of 2 factorial design. We have a 2, so means that you have 4 of them. Okay, you have a 2 power 2, then you have 4 of them. Then if you want to run in the block 1, you must choose a k or less than the k. So therefore the k the p is because the k is 2, so the p is only 1. So therefore you run is a 2 power of 1 is equal to the in the 2 blocks. Okay, it's 2 power of p in complete block. So therefore you run either the 2 blocks or in the 4 blocks where the p is equal to 2, then it's 2 power 2 is 4 and so on. Okay. So I show you how we want to do in the running the 2 blocks first. Then after that, only show you the example. Okay. So of course, if you run the less treatment combination, then you will lose certain information. This one is you need to pay off. Okay. So the compounding the 2 power k factorial in the 2 blocks. For example, if you have a 4 treatment combination where is a 1 A, B, and AB here. Okay, so certain quantity of raw material is to be tested in the batches. So for example, each batch of raw material is only large enough to run for the 2 treatment combination. Because you have a 2 power of 2, okay, you only can be run the 2 treatment combination in each block. So how are you going to assign it? So the 2 batches of the raw material are required. Okay. So in this case, the batch 1 will go for the block number 1. The batch number 2 will go to the block number 2. So you only need to run 4. Before that, for each block, you need to run 4. But now, for each block, you only need to run only 2. Okay. So we must assign the 4 treatment combination to each block. How are we going to assign? We can have a 1 and the A. Then the remaining one is a B and the AB. We also can have another combination B. Then after that, we have a A and the AB. We also can have another one is a 1 with the AB. Then the A and the B here. Okay, so which one are we going to choose? The block 1 is these 2, or these 2, or this one is here, or the different combination. Okay, so there are different combinations here. So how are we going to choose it? Okay, so the choosing of the treatment combination are important because they will decide which are the information you will you cannot get, or you're willing to lose that particular information. Okay. So here I will show you the examples of the block here. So if you're choosing the block 1 as a 1 and the AB, the block 2 is a A and the B. So this one we say that the AB is confounded with the block. Why we say that AB is confounded with the block? Okay, I show you in the diagram here. Okay, so now if I choose the block here is a 1 and AB, and then A and the AB here. Okay, so means that the first block you run these 2, the second block run these 2. So we say that AB will confounded with the block. So we from this diagram here. Okay, so the plus minus diagram is also the same thing. You have a 1 AB AB, the treatment combination of here. So if you can see that just now they choose the 1 and the AB and the A and the B together. Okay, so you check the sign. If they put the A and the B together, you can see if the A is here, they put this one and this one together. They put these 2 together. So you can check under the 1 and the AB, the sign is a positive and the positive, the same sign. Okay, both of them given the same sign. A and the B, the same sign. Minus. I don't care about whether positive or negative, but 1 and the AB, they are the same sign, positive sign. The A and the B is a negative sign. So therefore, they are confounded in the B. Okay, we call them, they confounded in the B. Sorry, in the AB. AB will confounded with the block if we choose in the following way. Okay, let us go through the second one. If we choose for the following one, for this thing, then we check it out. If we want to put the 1 and the A to 1 and the B together, A and the AB together, okay, so you just check the 1 and the B. So what are the signs are the same? Okay, this one is both of them negative. Okay, if you choose the 1 and the B together, here negative, 1 is positive, it's not working. Okay, it's no, they must be the same sign. Therefore, you can observe that both of them get negative. This one is both of them get negative. This one, both of them get positive. So we know that they belong to the A. So A will confound it. Okay, so similar to the above here, the 1 and the AB, 1 and the AB is a positive. This one is a positive sign together. This one a negative sign together. Okay, so this one is an example of the confounding. How are you going to do the confounding in the two blocks here? So the usual practice is a confound with the high order. Why we need to confound with the high order iteration? Why we do not want to confound the A? Okay, in this one is a 2 power of 2 factorial design, only 2 factor iteration. So we will choose the AB will confounded with the block. We do not want to choose the A confounded with the block, because if you choose the A confounded with the block, the information of the A, you can't obtain the information of the A anymore. Okay, but you must remember when you run the analysis of the two factor of the A and the B, you are interested about the factor A, whether the factor A is a significant or not significant. The factor B is significant or not significant. Then if you somehow you choose the A confounded with the block, means that the A information you cannot get anymore. So this one is do not help for your analysis. Okay, it's not your target, because your target is want to study about this factor. Then somehow you are confounded, you cannot find this information. So this is not the result what you want. Okay, so therefore here I mentioned to you that we will try to confound the high order iteration with the block, because a high order iteration is not the important factor you are interested on. You are interested on the main factors itself. Okay. So you can see another example is how I do the confounding. Okay, you of course you no need to refer to the plus minus sign there just now. Okay, I show you the example. It's a 2 power of 3 design. The 2 power of 3 design. So if you want to construct the contrast, you just put the A minus 1, B minus 1, C minus 1. Okay, you just multiply by this one. So therefore, if you expand it out, you will get the A, all the plus minus sign. Okay. So if you write it, okay, if you write in this way, then you can get the plus minus sign. Instead of you drawing the table, the factor A, factor B, okay, you list down all the 1, A, B, and so on. You list down all these things, okay? So instead of listing down all these things, then you can be use the following one to check the contrast. So I have shown it to you in the tables, the contrast there, okay? But you can be use the following way to calculate the contrast. So from here, if you want to know the ABC contrast, and then you want to confound it with the ABC, then you will just choose those of the sign together, they will put in the same block. The other one for the positive and the negative one. For this one is you put the negative one, all the negative together. This one is all the positive together. Okay, together. Then this one will be say that block 1 consists of the four factor treatment combination. Another one is a block 2 is treatment combination. Then we can say that ABC is confounded with the block. Okay. If you don't want to use a plus minus of here, of course, you will refer to the table here. Okay, if you want to do the confounding of the ABC, then of course the negative one, we group them together. Negative one is a 1, and then the AB, and then the AC and the BC will be this form. Then the remaining one, plus 1 is grouped to 1. Okay, so means that in your treatment combination, you only run 4 treatment combination under the first block. The second block will run another 4 treatment combination. Okay, so this one is called the ABC confounded with the block. Okay, so if you do the confounding of the block, then I will show you later on, you will lose the information. Okay, you will lose the certain information of the block in there. So let us go through one more slide here. This is the same diagram as just now. They put in the 2 blocks. Okay. So this one is an example of the here. You have a example here first. Okay. You have 4 factors here. For these 4 factors, you consist of the blocks. Means that the blocks can be the 2 batches of material. Then for each batch, you only run the 8 treatment combination. The remaining one, run another 8 of them. Okay, so you don't run completely. If you run completely, that one is a blocking design. You run all completely, you can get all the information. But now, if you want to use a confounding technique, then you only run less treatment combination within the block. Okay, so in this case, we have a 2 power of 4 factorial design. Okay, so if we want to run in the 2 blocks, so each block consists of the 8 treatment combination, 8 treatment combination. Okay, so because of the block here, then we can calculate the block effects. Okay, the block effects here is in fact is the mean from the first block and the mean for the second block. You just get the difference of that. Then you know that is from the block 1 to the block 2, the effect is negative 18.62. Okay, so this one is calculation of the just the average value here. You know the effect from the block 1 to the block 2. Okay. Furthermore, here the sum of square here. The sum of square after you do the confounding with the ABCD, because this one is confounding with the here they do the blocking here is actually they will arrange it according to the ABCD. Okay, confounded. Okay, they arrange this one in the form that ABCD were confounded. Okay, so if the ABCD were confounded, then all the plus, all the same sign, they will together. So if we want to calculate the sum of square for the block here, how we want to calculate the sum of square? Because we use a total square divided by the 8, the total square divided by the 8 here, minus a grand total square over 16. So you will get your sum of square for the block. But this sum of square for the block is in fact is the sum of square for the block plus the ABCD, because you confounded with the ABCD. Therefore, the effect of the block and the ABCD sum of square will be together. Okay, so this one is what I say, the information you will lose. So we go back to the just now the beginning. Okay, we go back to the here. Go back to the just now the beginning of the here. Here, if I do the confounded with the A as a confounded in the block, so means that the A factors or the sum of square for A, I can't find anymore. If I do the confounding here, the A here will be confounded in the block itself. So therefore, why I say that we always will be consider the high order iteration with confounded with the, so that the high order is not the important. Okay, you no need to care about it. Okay. So in this example, do the confounded with the ABCD. Therefore, the ABCD information is not important. You can be ignore this information. So these are the information you need to loss. Your information loss will be ABCD, sum or square for ABCD, because this one will be not important at all. So therefore, if you do the confounding, they will confound together with the block and the ABCD. So this sum or square is actually consists of the block and the ABCD together. Okay. Okay. So okay. Before I go through this one, you can see this one. Just now I mentioned to you that since the ABCD is confounded with the block, so the sum of square for the block will be equal to the sum of square for ABCD, will be equal to 1387.5625. So they were together. Both of them already is together. You can't differentiate which they come from the ABCD or they come from the block. They will be together itself. Okay. So I think maybe I will stop for the while first before we continue it. Okay, for the following one, I have a case 1 and case 2. Okay, we stop for the then we will continue back at the 8 o'clock or the 7:55. Continue. Now it's 7:25. Okay, I will answer one call first. Okay. Then after that we continue.